The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Our next presenter is Elizabeth Nadelman, and she's a materials engineer with Janney and Elstner Associates, where she has worked on a number of projects involving field lab and analytical investigations on concrete materials, structures, and pavements. She received her PhD in civil engineering in 2016 from the Georgia Institute of Technology, where she conducted research focused on knowledge properties and long-term durability.
Thank you for the introduction. Most of you probably saw in the program, Todd Nelson was supposed to be giving this presentation. He was unable to be here and sent me instead. I'm going to be presenting some of the work that we worked on along with our colleague Paul Krause, looking at some early age cracking in a number of bridge decks in Montana. This picture shown here is just one example of some of the characteristic cracking that we saw in these bridge decks, and to give you a little taste of what's coming up in this presentation, the bridge deck shown in the figure is only 5 years old. So just a brief outline of my presentation. I'll start by giving some of the project background, brief overview of our investigation. I'm not going to go into too much detail. I'm going to focus most of this talk on the thermal modeling that we did and also the recommendations that we made to the Montana Department of Transportation in order to help prevent and mitigate some of these issues in the future. So as a little bit of a background, Montana Department of Transportation came to us when they noticed severe early age transverse cracking on a number of bridge decks. In 3 of the bridge decks, there was deck penetrations, like I had shown on the first slide. And the biggest impact here was that the decks were only 1 to 9 years old. So this is approximately the location of most of the bridges. We looked at a total of 25 bridge decks. 22 of them were in western Montana in the Missoula area, which is circled here, and this is a fairly mountainous region. There were also a few bridges in Helena and Billings that exhibited similar bridge deck cracking that we did not investigate as part of this study. This is a photo of one of the bridges that we looked at. One of the things you probably will notice is this is in a valley. So the temperatures in this valley are going to range very widely in the summer months, which is when the concrete was poured, and also when we investigated these bridges, the temperatures ranged from about 40 degrees Fahrenheit in the morning to upwards of upper 80s to 90 degrees in the afternoon. We actually measured temperatures on the surface of the bridge deck during our investigation, which was in late August. Temperatures we recorded ranged from about 50 degrees to over 105 degrees Fahrenheit, so very wide temperature swings even in the summer months. The other thing I'd like to point out here is that the bridge decks were almost entirely replacements for bridges or bridge decks on bridges that were constructed in the 1960s through 1980s. I believe the one shown here was a 1980s bridge, but the original decks were all from the 60s through 80s, and the concrete was a new replacement made in the last 10 years. Typical distress patterns: in 3 of the bridge cases, we saw full deck penetrations, such as this one. You'll notice that there's a nice hole right here that goes all the way through the deck, and I'll show in a later slide the underside where you can see that hole. We also saw partial deck penetrations on some of the other bridges, and there was very frequent underside transverse cracking, also visible from the top surface of the deck. But on the underside, you can see a lot of efflorescence and very closely spaced transverse cracks. The bridge on the left is 9 years old, and the bridge on the right is the same one from that first slide that's 5 years old. So this is the type of distress you would typically see on much older bridge decks. but they were seeing them in bridge decks as young as 5 years old. So we were asked by Montana Department of Transportation to perform an investigation to determine the cause for this cracking and to also make recommendations to mitigate and prevent these cracks from happening in the future. So we performed detailed field investigations of 4 of the bridges in the Missoula area, and we also did a comparative investigation, more of a cursory field evaluation of 8 other bridges in the area. And our field investigations consisted of crack mapping, delamination surveys, concrete coring, impulse response, which we used to detect delaminations, and infrared thermography, which we also used for delamination and crack detection. And we also used a drone to get images of the underside of the bridge deck, and also had the infrared camera on it, so we were able to do some infrared imaging with the drone as well. We also did some laboratory evaluations, which I'm not going to go into a whole lot of detail here, but they consisted of petrography, mechanical property testing, thermal property testing, and a few chemical tests to determine chloride ion contents and the composition of the efflorescence that we saw on the underside of the deck. What I'm going to focus on most today is the sensitivity analysis and thermal modeling that we performed. But first I'll go over a little bit of what we saw in the field investigation. So these are some of the characteristic crack patterns that we observed while we were actually out in the field. On the top, you see quite a bit of map cracking, which we noticed on a number of the bridge decks. Our petrographers and subsequent laboratory analysis, we determined that that was mostly due to plastic shrinkage. It was especially pronounced in bridge decks that contained silica fume. Then there's the transverse cracking, which I hope is visible to most of you in the audience on this slide. If it's not, it'll be much more apparent on the next slide. But we saw much more frequent transverse cracking on a number of these decks, approximately 2 to 4 foot spacing at the worst, though in some cases they were as closely spaced as 6 inches from one another. This particular bridge that I'm showing here is 1 year old. The cracks are actually sealed, which makes it easier to visualize. These sealants were applied within the first month before the bridge had even opened to traffic, and all of the sealed cracks were 10 to 15 mils, 10 to 15 thousandths of an inch in width. So pretty wide cracks. They were spaced about 2 to 4 feet in some cases on this bridge that's only 1 year old. The most interesting type of crack pattern we noticed is what we're calling jump cracks. And what these occurred, or where these occurred, were where 2 parallel transverse cracks were very close to one another, typically about 6 inches or less. And it ended up that the crack from one transverse crack intersected the other. And they formed what we're calling these jump cracks. And when these jump cracks intersect like this in the figure, on top and bottom, that's where we suspect the holes that we had seen formed. So our theory based on our field and laboratory investigations, first is that the transverse cracks develop very early. Our petrographic analysis indicated that the cracks were very early in origin, not only because they were observed by the DOT at 14 days or less, but also because they tended to wind around the aggregates. The cracks progress over time, and so as you see in this figure, they typically originated right around the girders and then progressed outward from there. When they get closely spaced, like shown here on the left, that's where the potential for jump cracks happens, and you can actually see a jump crack forming here on the right. And then if the jump cracks become continuous, that's when the holes can develop. So we wanted to determine what's actually causing these early age cracks to develop. We did a number of material tests and examinations, and we determined that one of the most likely causes, or 2 of the most likely causes, are temperature and shrinkage sources. So we did a thermal model. We had a temperature model that we used Concrete Works for. And we also made a very simple stress model. It's more or less hand calculations that we performed in MathCAD based on an analysis from the 1960s by William Zuck. In our temperature model, we used Concrete Works to simulate peak temperature versus time histories for 3 of the bridge decks we looked at. We took the deck geometry based on the bridge drawings, and we estimated or simulated the heat generation in the concrete due to hydration based on the mixed designs and cement compositions that we were provided by the DOT. We took records of ambient temperature, wind speed, and solar radiation and actually input them into the model. And these records came from the National Climatic Database Center. And we assumed a placement temperature of 65 degrees for all of the concrete batches, which was based on limited batch ticket information that was available to us. So I'm just going to show an example of one of the outputs from our thermal model here. This is for what we called Bridge 6. And the 2 curves I want to point out first are this gray dashed line and this black dashed line. The gray is the ambient temperature at the time of the bridge construction, and the black is the simulated temperature history, peak temperature history in the bridge deck based on the actual placement time of 7 a.m. And what you can see is that about 24 hours in, we have a very large difference between the temperature of our concrete and the ambient temperature. It's about a 35-degree difference. And we saw these same effects for the other bridges that we modeled. So this is Bridge 1, and you see a very large difference about 24 hours in. And we saw the same thing for Bridge 2, about 24 hours in. Now the other curves I want to point out are these colored ones. We also decided to simulate other placement times. So in blue, we have a 6 a.m. placement time, which naturally would look very similar to the 7 a.m. placement time that we have in black. In green, we have a noon placement time, and you see that the peak is starting to shift. And when we start placing in the late evening with this red curve here, which is a 6 p.m. placement time, what you see is that the peak temperature occurs a full day into the hydration cycle, and it occurs at a later time, which means that the concrete has had greater time to develop tensile capacity. So it can actually handle these differences much better. The other thing that we did was look at stresses, and these are approximate stresses. We had to make a lot of assumptions in our model because we don't have a lot of the early age information from this bridge, or these bridges. But we did some basic first principles stress calculations based on the model by Zook. And Zook's model was developed for composite bridge decks. So essentially you have a girder and a deck. And the way that the approach is you calculate the free strain in both the girder and the deck due to temperature change or shrinkage or both. And then you can calculate the stresses in the bridge deck using compatibility equations right along the boundary between the deck and the girder. So it's a very simple approach. It's based on very basic principles. We took that a little bit further, and we split the deck into 3 sections because we wanted to be able to model the effective temperature gradients that are more complex than just a uniform temperature change or a linear temperature change. So we divided the deck into 3 sections, but the same principles applied. We used compatibility at all of the interfaces to make sure that the stresses that were generated are, or to calculate the stresses that were generated. And they also modified the model by incorporating creep into the model. And this was done implicitly. We basically assumed that at very early ages, the elastic modulus was half of what it actually was. And that's because if you assume the full elastic modulus, or without accounting for creep, it's essentially like saying you're taking your concrete and placing it in a freezer. It's a shock load. It's going to contract much faster. But these are more gradual temperature changes. And so the effect is not going to be as severe as if you were to take hot concrete and stick it in a freezer. It's going to change gradually. And so you can accommodate this by reducing the elastic modulus. So at early ages, we assumed the elastic modulus was half. At later ages, we assumed it was 1/3 of the actual value. And again, because we had to make a lot of assumptions in this model, we focused primarily on a sensitivity analysis. We wanted to understand what factors could contribute the most to the cracking potential at these ages. So we looked at a number of factors: autogenous and drying shrinkage. We looked at temperature changes in the deck and the girder, and we looked at both uniform and linear temperature changes there. And we also looked at compressive strength of the deck concrete, the thickness of the deck, and the girder spacing. I'm going to focus primarily on the first three of these, the shrinkage and temperature changes, just because they are the more important factors here. And what our findings showed were that the high sensitivity to the tensile stresses, there was a higher sensitivity to tensile stresses that was caused by early age temperature drops. So that initial temperature decrease from the hot temperatures of the concrete after hydration to the cooler ambient temperatures. The bridge deck stresses were very sensitive to that temperature drop and similar temperature drops. We also found that stresses due to thermal gradients, which might occur, for example, by cooling the surface of the bridge deck, were greater in magnitude generally than stresses that were due to uniform temperature changes. So being able to model those thermal gradients was actually very important in determining what stresses are more likely in the bridge deck. We also found that the strains due to temperature were generally larger than the strains due to autogenous shrinkage at early ages, because the autogenous shrinkage is a much smaller stress in general. It was about 30 psi at the maximum for most of our simulations. And finally, we found that drying shrinkage might be significant at later ages, though it's not really important at the earlier ages. Finally, once we had done those sensitivity analyses, we did some approximately realistic temperature distributions. I'm putting that in quotes because, again, we don't really know what the situations were like at the time of the bridge construction, so these are just approximate, but they're more realistic than assuming an arbitrary number. So what we found, or what we simulated first, was we assumed that the top third of the deck was cooled 10 degrees cooler than the interior of the deck. And what the simulation showed was that we were generating tensile stresses up to 130 psi after just 3 days. And just as a comparison, the tensile strength of the concrete at this age could be about 300, 350 psi. So just this 10% difference at the top surface of the deck is enough to cause about 50% of that tensile stress to be generated. But we can also see steeper gradients may have existed in the actual bridge deck, which may have substantially increased those stresses. The other thing that we found was that, or other simulation we performed, was to look at the effect of a uniform drying shrinkage of 500 microstrain. This would typically happen much later in the bridge deck life, obviously, not in the first 3 days. But in this case, what we found was that the tensile stresses under this assumption could reach up to almost 600 psi, which is very much closer to the tensile capacity of the concrete. And remember, these are additive, so if we have a thermal effect and a drying shrinkage effect or an autogenous shrinkage effect, those strains are going to add to one another and the stresses will more closely approach the tensile strength of the concrete. So what we found from these simulations were that the tensile capacity of the concrete may actually be exceeded by some realistic thermal and shrinkage effects. And the other thing that we noted in these simulations was that the stresses that we calculated generally correlated with the observed severity of cracking in the actual bridge decks. So based on our modeling and our field investigation, we proposed a few recommendations to the Montana Department of Transportation. The first set were to limit the risk of thermal cracking. And the two recommendations we made to them were to move the pour times to later in the afternoon so that the peak concrete temperatures didn't coincide with the coolest temperatures of the day. Instead, the peak concrete temperatures are going to correspond with the peak temperatures the following day. And that would limit some of those early age temperature differences that we were seeing. The other recommendation was after the peak hydration temperature was reached to apply insulation with curing blankets. And Montana actually implemented these recommendations on 2 bridge decks in late 2016 and on 3 new bridge decks in 2017. And they've reported to us that they've seen little to no transverse cracking. And typically, if they do observe cracks, they're usually over the bents or piers where the restraint is much higher. They sent us this photo of one of the bridges shortly after they removed all of the formwork. And this is the insulation and curing. And this is typically when they would go out and seal all the cracks. And they sent us this photo to say we didn't have to seal any cracks. So Todd has also been out there. Todd Nelson, who was going to give this talk, he went out about a month ago and also did a walk through one of the new bridges that was done this way, and he did not notice very significant cracking at all. He saw a few hairline cracks, and that was it. We also made a few other recommendations to limit some early age shrinkage cracking. We had talked about before, we saw some evidence of plastic shrinkage, and there was one bridge that had some evidence of autogenous shrinkage as well. So our recommendations to reduce some of the early age shrinkage cracking were to immediately fog mist the concrete until wet curing media was able to be placed. This was not part of their current curing specifications, but they're going to be adding this to it. We also recommended limiting the cementitious material contents to 600 pounds per cubic yard or yet less. Some of these mixes had very high cementitious materials contents, which only exacerbates a lot of those early age shrinkage problems. We also recommended limiting the silica fume replacement level to 5% to help combat some of that early plastic and autogenous shrinkage. And we also specified a maximum water cement ratio between 0.42 and 0.45. A lot of these bridge decks were designed at much lower water cement ratios, like 0.36. And at those levels, autogenous shrinkage can become impactful as well. So these were really focused on autogenous shrinkage there. Our final recommendations to them were to increase the design thickness of the decks to 8 inches minimum. A lot of these bridge decks that we saw that had problems had decks that were as small as 6 inches in thickness, though we also did see issues in bridge decks that were 9 inches thick. But our stress analysis indicated that the thicker bridge decks helped reduce some of those stresses. And finally, we recommended that they modify the specifications to require staggering of the top and bottom transverse reinforcing mats, because as we saw in that very first photo, if they aren't staggered, then holes can develop and the concrete can go right through. So just to summarize, we found that early age thermal effects can generate significant thermal stresses in the bridge decks, and that the risk of thermal cracking, at least, may be reduced by placing the concrete later in the afternoon and applying insulation to the deck after the peak hydration temperatures are reached. So with that, I'd like to thank you for your attention, and if anyone has any questions, I'd be happy to answer them.
Yeah, thank you. I mean, that was an excellent presentation. I just had a couple of quick questions. Did you look at whether there were any differences in the curing methodology at all, and presuming it was curing blankets with continuous source of moisture?
All of these bridge decks actually had the same curing practices specified. Typically what they do is apply a moist cure wet burlap after set, but they specified fogging and misting, but usually that wasn't necessarily enforced.
Sure.
And they had 14-day moist cures with wet burlap typically.
Yeah. What we've seen problematic in the past is when it's allowed to dry out, there's evaporative cooling, which actually really exacerbates the surface. But the other part I was wondering is whether you looked at the formwork at all and whether there was actually any kind of steel bracing beneath the formwork that may have acted as heat sinks at the soffit of the deck at all that could have exacerbated the thermal shock.
We didn't look at the formwork particularly for these bridge decks. That information wasn't available to us, but it is something that we have talked with the DOT about looking into in the future.
Very nice job. You did. You presented very clear. The only question I had was with the effect of creep. Mm-hmm. Were you using creep on the shrinkage data, or were you using a creep on everything?
It was on everything. So the way that the model works is it doesn't really distinguish between thermal effects and or thermal strains and creep strains. It essentially calculates a strain and then calculates stress by multiplying by the modulus.
Yeah, because the thermal temperature changes daily are a lot faster, and so those can be almost elastic, cause almost elastic stress levels. But you can drop a lot of stress off from drying shrinkage because it goes over such a long time.
Right, and we actually considered that in our discussions when we were working on this model. What we felt was it was more conservative to assume that there was going to just be creep in everything. That way we're estimating lower stresses, but we're still seeing that these stresses can be significant.
Yeah, it was very good to move the time the placement time back so that you're matching the heat liberation from the cement with the ambient temperature. So that's a key thing that a lot of people miss.